My name's Jill Watt. I'm Director of the Foundation Alumni and Events team, and I'm joined today by my colleague Lynn Robertson as well from the events team, and between us we're just looking after sort of the housekeeping, if you like, of today's event. We would just kindly ask that you remain on mute throughout the talk. There will be an opportunity to ask questions at the end, and should you wish to do so, you can put them to today's speaker in person. If you're comfortable in doing so, we would ask you to keep your cameras on. I think it's always nice for the speakers to be able to see your faces and see your reaction to the talk. So if you're comfortable in doing so, that would be great as well. When it comes to the Q&A at the end, you can submit questions either via the chat functionality. You can be submitting those questions at any point throughout the talk. Lynn and I will be picking those up and just keeping a track of those so that we can facilitate the Q&A at the end. The other option is to use the raise your hand functionality. So when you go into the chat option at the bottom of your screen, you will see that there's a raise your hand functionality. So if you want to raise your hand, then Lynn can invite you to ask your question in person as well. So you're welcome to do that. For now, I'm going to hand over to Professor Cam Donaldson, our Pro Vice Chancellor for Research, to deliver today's welcome. Thank you, Cam.
Thanks, Jill. As ever, as Pro Vice Chancellor Research here at Glasgow Caledonian University, it's my great pleasure to welcome you to this series of professorial lectures. This is a series that reflects the public role of universities, which for Glasgow Caledonian as the University for the Common Good is about how our research and our teaching contribute to the Sustainable Development Goals issued by United Nations in 2015, running through to 2030 and applying to all countries. And tonight, with a focus on bioengineering, several SDGs will be touched upon, but especially those that are obviously most closely related to the environment. These professorial lectures present an opportunity for recently promoted professors to showcase their previous work and future plans to colleagues, other stakeholders, to friends and to family. And Bobby has with him online today some international eco-engineering colleagues. His family will be watching a recording, so whether now or indeed later, I just wanted to record the fact that you are all most welcome to this lecture. And I would also like to thank Bobby for being first in line in our new online series of these professorial lectures. And so to Bobby himself. So Slobodan Bobby Mickovski originally studied civil engineering at St. Cyril and Methodius University in Skopje in the then Republic of Macedonia, before heading to University of Manchester, where he graduated with an MSc in Environmental Sciences and Policy in 1999 and a PhD in Plant Sciences in 2002. And via research positions at the Institut National de Recherche Agronomique, Bordeaux, University of Dundee, and then at Jacobs Engineering, where he was a principal geotechnical engineer, Bobby arrived at Glasgow Caledonian in 2012 as a lecturer. He became a reader in 2014. Bobby's work on ground bioengineering has been published in top environmental, geotechnical and hydrology journals, presented at top venues and conferences internationally, with his research having been funded from various industry and other competitive knowledge transfer and European Commission funding sources. His work is award-winning, as recognised by the Chartered Institute of Building and the European Soil Conservation Society. Bobby's future work is set to critically review how recent civil engineering and research projects address climate change challenges such as erosion, shallow landslides, and flooding, benchmarking them against the SDGs. Bobby was promoted to his Professorship of Civil Engineering and Environmental Technology in 2017. And in celebration of that, today, Bobby's going to look at how academic research in ground bioengineering has been focused on determination of the strength, stability and sustainability that vegetation provides for the soil and the wider environment it grows in. Please join me in welcoming to the floor to present his lecture on Soil is the Route to a Solution, Professor Slobodan Mickovski. Welcome, Bobby.
Thank you very much. Thank you for the great introduction. Welcome, everyone. Good evening. It will be my immense pleasure and honor to speak to you tonight on a subject that is the center of my research and my pet subject, which will be basically designed with vegetation for sustainability and resilience against climate change. So to avoid any issues with connections, I will just start and present part of my experience on this topic and hopefully outline a little bit my vision for the future of greener civil engineering, if you like. So before we enter the design sphere, please let me build up a niche for this talk by introducing few concepts and explaining what they mean in relation to the topic of this talk. Green infrastructure, usually defined as a network of natural and semi-natural areas, which is strategically designed together with other environmental features to deliver a wide range of ecosystem services. Now, this network in general comprises green features, where terrestrial ecosystems are present, and or blue features, where aquatic ecosystems are present, and other sometimes gray or traditional engineering features. The difference between the green and the traditional gray infrastructure is that the green is rich with biodiversity, which in turn can be used to perform a variety of useful functions, including engineering. And all of this is for the benefit of not only nature, but also people and economy, i.e. sustainability in general. Assigning an engineering function to the vegetation within a live infrastructure system, if you like, has been the basic concept of soil or ground bioengineering, sometimes also termed soil and water bioengineering. Now, using this concept, which combines scientific and practical knowledge and skills for ecosystem management and benefits to the natural and man-made environment, the vegetation is employed as a building material, contributing to natural hazard control and mitigation, as we said, erosion, flooding, landslide, and similar. Within this concept, nature-based solutions, or NBS, are employed for sustainable management and use of nature for tackling socio-environmental challenges, including climate change, water security, water pollution, food security, human health, disaster risk management, and similar. The existing European Green Infrastructure Strategy aims at ensuring integration of green infrastructure in spatial planning and terrestrial development. So it's promoted through different policy areas such as regional cohesion, climate change, environmental policies, but also disaster risk management, health, consumer policies, and importantly, the common agricultural policy. The current experience shows that ecosystem-based approaches such as the green infrastructure or nature-based solution, soil water bioengineering are cost-efficient policy tools, but they're not used to their full extent, and their potential should be further strengthened at national or transnational level, perhaps through integration of the engineering components, for example, standards, best practice, learning, etc., within the existing policy instruments. It is within this typological hierarchy that we find the design with vegetation as an essential and very important part which needs more attention and definitely full consideration. In 2015, the United Nations set out 17 Global Sustainable Development Goals, SDGs, with some 169 sub-targets, most of which directly or indirectly connected to some form of infrastructure. Considering the fact that the built environment and construction industry employ significant portion of the workforce globally, it is essential to understand that sustainability for the infrastructure can only be achieved if the elements associated with it, such as people, environment, physical infrastructure, are supported and sustained. As our built environment and the wider economy become more information-based, associated softer infrastructure will be required to keep pace. In particular, new frameworks, organizational structures, and business models will be required to understand, plan, manage, and regulate the green infrastructure and the related data infrastructure in order to ensure stability and resilience. Stability is the resistance offered by a structure or a system to undesirable movement like sliding, bearing, overturning, etc. While resilience is the ability to absorb or avoid damage without suffering complete failure. Both of these concepts apply to both engineering and social and natural systems. What would be then the hierarchy of design requirements, bearing in mind the concepts that I've mentioned previously there? Well, the engineering design traditionally focuses on the stability of the structure or the system. However, higher value from the engineering design could only be achieved if sustainability and resilience are incorporated in the design. This is reflected by the relatively recent introduction of sustainability and resilience standards and the pursuit of nature-based solutions, which by definition would be sustainable and resilient. The origins of design with vegetation can be traced as far back as the ancient civilizations in the East, including, for example, here China, where a sao signified a mixture of stems and branches of willow and crushed rock, all of them tied together with twine or bamboo rope. In the 1st century AD, it was recorded that one of the great emperors of the Han dynasty ordered his soldiers and generals to transport saos to fix the breached levees of the Yellow River and stop the flood water. We know this because a section of the Sao reinforced levee of the Han dynasty was discovered in 2005 along the Bar River, so it survived that long. Now, cutting through the ages slightly more roughly than characters like Kubrick or Leone, to the 20th century in Europe, where the tradition of using vegetation for civil engineering purposes has survived, mainly in the Alpine countries and the Mediterranean. All of them regions still suffering from hydrometeorological hazards such as landslide, flooding, or erosion. The last 25 years have seen a revival in the use of vegetation for civil engineering purposes, either as a standalone technique or in combination with traditional civil engineering materials and techniques. This revival coincided with the quantification and appreciation of the hazards facing our planet due to climate change, bringing the sustainable use of vegetation to the fore of the preferred techniques to combat geoclimatic hazards. Now, I see ground bioengineering design as a journey of rediscovery of the full greatness of technological achievements and thought in engineering, as well as an endeavor to compete with these achievements on an ideal plane. This ideal plane can be slope stability, where major tree roots act as mini piles or soil nails. It can be soil strengthening, where the small wiry roots penetrating the soil create a composite reinforced material. It can be drainage using the evapotranspiration potential of vegetation. It can be provision of habitat, biodiversity for conservation purposes, or it can be a combination of all of this and much, much more. The combination of these effects make the vegetation conducive towards addressing the SDGs on climate action by enhancing the resilience and adaptive capacity of infrastructure to climate-related hazards and natural disasters globally. These hazards include shallow landslides, flooding, erosion, as I said, which are expected to become more frequent in the near future. These hazards can originate out with the infrastructure or within it and affect not only infrastructure users, but also construction workers and the general public. Due to the increased likelihood and the potential severity of these hazards, there is a need to integrate climate change measures, especially the ecosystem-based climate actions, such as green infrastructure, nature-based solutions, etc., into national, international policies, strategies, and planning, but also to improve education, awareness raising, and human and institutional capacity on climate change mitigation, adaptation, and impact reduction. Recent years have brought many green infrastructure projects into the eye of the professional and general public. To illustrate this, I will use the information gathered through a recent transnational project I participated recently, the ECOMET project, which was financed by the European Commission with an aim to generate new alliances and dynamics between the academia, research institutes and industry. The case studies we reviewed in this project include soil and water bioengineering projects in fluvial, coastal or montane environment. They range from riverbank stabilization through coastal dune management through slopes in transportation. The common denominator of all of these projects is the sustainable use of vegetation for civil engineering purposes. The generic types of structures, eco-engineering structures, soil and water bioengineering structures, play to the strengths of vegetation to reinforce the soil and push back the potential failure plane and or provide efficient drainage, but also potential for evapotranspiration. The brush layering technique on the, for example, or shown on the left here, closely resembles reinforced soil construction. The stability of the structure is secured by the strength of the live and inert materials applied. Similarly, the live drain in the middle closely resembles the filter drain construction. In the former, the live material ensures the necessary permeability of the drain by providing preferential drainage paths along and among the bundles. The live retaining structure, such as the live crib wall on the right, also well known in civil engineering, but this time with a difference. And the difference is made by the live materials allowed to grow and provide reinforcement beyond the original geometry of the structure. The added value of these typical eco-engineering structures is their capacity to provide sustainability and resilience. Environmentally, they provide biodiversity and habitat for the flora and fauna. Locally available materials can be used in the construction of these structures, which can also combine traditional structural materials and other biodegradable materials. These two, combined with the social acceptance of the aesthetics, add major sustainability value to the eco-engineering structures. The resilience of these structures is provided by the living elements in them and can be demonstrated in the longer term when the inert materials would lose strength due to natural processes and external loads, but the structure will not collapse because the loads are now transferred onto the vegetation, which will provide a more ductile response to the loading conditions. One example of eco-engineering practice for riverbank stabilization is shown here, courtesy of our friend and colleague, Klaus Peklo, who contributed to the ECOMET project, where you can in turn find further details of this work. Brush layers you see here are constructed along a stretch of a riverbank that supports residential properties. Note the flexibility of the construction technique, which allowed forming the riverbank curve in line with the hydrological modeling, and the use of pioneer vegetation, which allowed for quick recovery of the ground cover and only in few growing seasons provided habitat for the local fauna, which returned to the site. Not to mention alleviating the fears of the local residents when it comes to collapse of their property. The second one I have here is an example of an eco-engineering used as a supplementary technique to the traditional civil engineering works. To stabilize a slope periodically undermined by a dynamic flash flood fueled stream, our colleagues from Gembuild in Italy designed a type of gabion wall which in the long term will prevent progressive slope failure due to geoclimatic effects while providing aesthetic value for the community. The permeability of the structure governed the design solution, which had to provide enough pore space and capacity to allow water flow, but also enough moisture retention to allow for root growth. The photo taken few growing seasons after construction shows that the trees planted at the toe of the slope have prevented scour while acting as toe reinforcement. Native vegetation colonized the structure at height, and you can see here the progress of this colonization by the different vegetation types inhabiting different layers of the structures. You can find more details on this project on the ECOMET webpage. Finally, I want to show you that eco-engineering techniques are often applied for erosion protection in a coastal environment. In this example from Portugal, details of which are also available on the Ecomed webpage, you can see the planting technique applied in situ and combined with construction of a sediment control barrier made of inert, locally available material. The wind erosion, which was the major geoclimatic hazard on the site, is controlled by the sediment trapping capacity of the inert material until the planted material is strong and high enough to take over this function. The overall sustainability of the beach as an ecosystem is achieved with the choice of native vegetation and the resilience by protecting the planted material with an inert material until the necessary strength and geometry are achieved. In the current ground bioengineering practice, at least across Europe, the scientific research has rarely been reconciled with the engineering approach toward design and construction. This has led to inability to scale up the biological and physico-chemical effects of vegetation or choosing appropriate vegetation for mitigating different climate change effects when it comes to design and construction. On the other hand, the engineering design aspects have not been taken into account when investigating the ground bioengineering systems and their components. All of this have resulted in a slow uptake of this approach by the construction industry and overshadowed the urgent need of achievement of the SDGs across the whole life of a ground bioengineering project. To explore the viability of the ground bioengineering as an effective approach for combating the effects of climate change and to highlight the areas where civil engineers should focus in adopting this approach, I tried to analyze the set of successful and less successful climate adaptation case studies across Europe provided by the partners of the Ecomed project against the project life cycle stages and to highlight the existing knowledge as a basis on which civil engineering engineers can build on with innovation in order to respond to the global climate change challenges and the achievement of the SDGs. Taking the RIBA plan of work stages as a basis for mapping the experiences of eco-engineering design, we asked the academics, researchers, industry professionals to outline the design process they have participated in. Based on these records, we identified a number of gaps in the knowledge and application which will have to be addressed before we can talk about ground bioengineering design in a civil engineering design language, if you like. For example, the major gaps identified included lack of appropriate ground investigations, lack of maintenance, lack of monitoring provisions, lack of suitably qualified workforce, and low stakeholder engagement throughout the project life. In the following slides, I will guide you through the project stages, reflecting on the civil engineering design in light of the achievement of the United Nations Sustainable Development Goals. The civil engineering design is the art of the possible, if you like, and its success is measured by the degree to which the engineer has explored the limits of what was possible under a particular set of circumstances, structurally and aesthetically. Successful and innovative design starts with assigning engineering function to the vegetation. This function could be to reinforce the soil, stabilize the slope, retain sediment, attenuate runoff, or similar. Furthermore, this function could be achieved with only vegetation or in combination with traditional civil engineering materials and techniques. And a broad agreement on this choice and effective communication with the stakeholders is also essential at this stage. With this, we can avoid marginalization of the vegetation to aesthetics only, landscaping only, while utilizing all the engineering properties it can contribute to the stability of the structure and the sustainability of the environment. In order to inform this very important decision, a suitable hazard and risk assessment should be carried out. The process is similar to what we are used to in traditional civil engineering, with small differences in accounting for the effects of vegetation. To highlight the sustainability and resilience the vegetation can contribute to, the driver would usually be an effect of the climate change. For example, an increase in precipitation volume or a change in the rainfall pattern, and the risks which pertain to the vegetation would include short-term, long-term stability, which will capture the temporal changes, for example, the growth over time, and also sustainability, which would capture the plans for creation of habitats, enhancement in biodiversity, provision of recreational facilities, carbon footprint, etc. During this stage, the pros and cons of using vegetation in the design should be carefully weighed up. For example, eco-engineering is considered to be cost-effective, eco-friendly, aesthetically more acceptable, providing soft finish, but due to the nature of the materials used, it might require maintenance in the short term, or more input parameters for numerical modeling of its effects. The balance will be different in different projects, but if the stakeholders agree on an objective to provide a solution which will be more sustainable in the future, there will be a high probability that a green solution will outweigh a gray solution. To capture this in contractual terms, the pre-qualification and quality submissions at tender stage should comprise an assessment of sustainability of the proposed actions by the tenderers against generic and specific climate change challenges associated with the project, as well as a commitment to a minimum site disturbance during demobilization and the defects correction period. The evidence of the effects of ground bioengineering approach against the effects of climate change, presented not only here but also in the published literature, should motivate the engineers to embrace this approach from the inception or feasibility stage of the project. The eco-engineering designer needs to have a bold analytical mind and be ready to always discard conventional solutions if better, more sustainable ones could be devised. Once the engineering problem is identified and a connection is made with one or more climate change related hazards, the range of potential engineering solutions should include at least one where an engineering function is assigned to the live or green part of the solution, of the structure. These considerations can be made on the basis of existing successful or unsuccessful case studies, experience as well, but will have to be contextualized with preliminary investigations specific to the project location and environment. Such investigations would include not only the standard geohydrological or environmental investigations, but also investigations into the mechanism through which the live element is to provide the engineering function and the biological constraints associated with the potential solution. Here, I give you an example of a non-intrusive radar investigation we carried out in situ in order to establish the root system morphology, so we can then model the stabilizing effect we could expect from similar vegetation across the site. These investigations can be easily appended to the standard set of preliminary investigations and will allow not only easier quantification of the contribution of the live element, but also knowledge transfer between academia and industry. If the project is of a larger scale or conservation-based, for example, a prioritized action framework, as well as mapping and assessment of ecosystems and their services, can be done in accordance with the European directives. This is a very good opportunity for a civil engineer to enter ground bioengineering planning at a strategic level, because with the exception of Germany's national green infrastructure concept, the European countries have not yet adopted national strategies specifically dedicated to green infrastructure. Now, ground investigations are likely to provide us with a range of parameters which can be used in the specimen design. Both specimen and detailed design, however, need to take into account the major effects of vegetation, which can be broadly divided into mechanical, hydrological, and environmental. The main mechanical effects of vegetation are usually the reinforcement the small roots provide to the soil and the ductility the roots provide during shear failure. Previous research carried out in situ and in laboratory indicates that smaller roots contribute towards an increase in cohesion of the root soil composite. The magnitude of this cohesion varies with vegetation type and age, as well as depending on nature of the failure. Here you can see an example of an in situ measurement of root soil reinforcement and thus cohesion we did with colleagues from France some time ago in China. We also sampled rooted soil in situ and tested it in the laboratory to quantify the root reinforcement, which you can see in the shaded area in the graph in the middle. We also tested the roots in tension. This is a stress state expected during pullout caused by shear failure, for example, a landslide. Root tensile strength and their distribution laterally and with depth which can be determined using specific ground investigations I mentioned in the previous slide, can be used to calculate the root added cohesion. A number of routing models exist and can be used, but for example, Wu's routing model lends itself particularly well to the civil engineering rationale. It requires minimum vegetation parameters as an input, but we are yet to synchronize it with the civil engineering standards in terms of determining a consistent set of partial factors for its application. The relationships shown here on the graphs on this slide effectively confirm that the small roots provide resilience for the root soil continuum in form of an increase in ductility, which means that rooted soil is capable of withstanding larger displacements without catastrophic failure. On a larger scale, this would demonstrate as a creep in the soil on a slope being held by the roots. This condition would allow time and opportunity to the engineer to mitigate the effects of this failure as observed on different sites across the globe. Also would allow time for the vegetation to grow new roots, which would adapt to the new condition and then further stabilize the soil and continue to provide adequate habitats on land or near water. When we talk about water, let's touch on the hydrological effects of vegetation. They were historically much less understood and were neglected due to the misconceptions. For example, the vegetation behavior during the winter period. Namely, the above ground parts of the vegetation intercept and attenuate the precipitation that would otherwise reach the ground immediately. This effect is potentially best used in green infrastructure design solutions like green roofs, for example, where the selection of vegetation type combined with a suitable, potentially recycled substrate can provide a thriving environment for both flora and fauna while regulating the peak runoff and also providing a source of grey water for a building. The roots, on the other hand, use the water available in the ground, which can be groundwater, but also any precipitation that percolates into the ground, and through the process of evapotranspiration, effectively pump this water in the above ground part. What the evapotranspiration leaves in the ground is a state that resembles sucking out water through a straw from a glass full of ice cubes. The particles will get close together and adhere to each other due to matrix suction. The matrix suction, or negative pore water pressure, which demonstrates itself as an additional cohesion, will give additional strength to the soil, which then helps in reinforcement and stability problems. The magnitude of this contribution can be established using ground investigations and testing, both in situ and in the laboratory. We have shown that a relatively simple in situ setup, shown on the left here on the slide, can provide invaluable long-term information on the variations of matrix suction in vegetated soil. This kind of investigation, coupled with the laboratory testing on a micro scale, helped us to understand the temporal changes in matrix suction, i.e. the behavior during wetting, which simulates autumn-winter conditions in the Northern Hemisphere, and drying, which simulates spring-summer conditions. We found out that the best hydrological effects can be expected from vegetation somewhere between the wetting and drying periods, which coincidentally or not, is also the best time for the plants to grow. We also found that vegetated soil has a suction stress function that is distinctly different from the one of fallow soil, which is known in geotechnical engineering. This function is governed by the soil's hydrological regime, and it can be used as a proxy to quantify the plant-derived hydrological reinforcement of the soil. Based on these considerations, you can see that it is of a paramount importance to specify hydrological testing of the vegetation in longer term if we want to take into account the vegetation effects in the engineering design. To outline and quantify the environmental effects, on the other hand, we need to think of the hydrometeorological hazards as drivers of local disturbances on our sites. These can be disturbances of the types of shallow landslides, for example. These, although unwanted from an engineering perspective, occur regularly and foster the evolution of slope landscapes as part of their self-regulating capacity. Hence, Gaining insight into how slope ecosystems function and evolve could make eco-engineering interventions on slopes more successful. The investigations we did on a coastal slope with a history of failure in Aberdeenshire confirmed that shallow landslides contributed to biophysical diversity, but also created distinct slope habitats within that landscape. Habitat differences in terms of species richness and compositions were a direct consequence of the slope self-regulation. Practically, this means that the natural resources are more depleted at the crest, where the failure originates, and most abundant near the toe, where the sediment deposition takes place. What this means for design is that any intervention near the crest of the slope will have to be focused on vegetation able to thrive in a harder, nutrient-depleted soil, but also able to provide a quick and versatile habitat. On the other hand, diametrically different, the nature-based solutions aimed at the toe of the slope will have to account for softer, richer, wetter soil, which already provides some biodiversity and habitats. Other environmental effects we observed on our site included burrowing animals re-inhabiting the slope after remediation measures for groundwater control were put in place. While NBS were employed to control the seepage visible somewhere at mid-slope, the wildlife inhabited the drier parts above the seepage line, and with burrowing created potential preferential drainage paths for surface and groundwater. Thus, we gained on the biodiversity and habitat creation, but potentially lost on engineering stability. However, the overall effect of the application of NBS has so far been positive because the recolonization of the slope by vegetation has managed to effectively control the engineering stability of the slope by decreasing the groundwater levels while providing soil reinforcement. These insights will be useful in slope restoration, particularly in harmonizing effective NBSs with the functioning of landslide-prone ecosystems. Once the vegetation effects have been accounted for on a micro or mesoscale, we can upscale to slope scale, catchment scale, in order to review the hazards and risks, to model the behavior of the nature-based solutions in place, and to assess the environmental effects. Apart from comprehensive ground investigations and understanding of the mechanical and hydrological effects of vegetation on a small scale, the engineer here will need tools like geographic information system, data from longer-term monitoring in situ, so relevant. In the example presented here, we have combined the hydrological hazard assessment based on the hydrology and topology of the site with the slope stability assessment, which is based on the geology and vegetation cover of the site, and produced a risk map which shows the areas prone to instability, areas at the highest risk. Multidisciplinary modeling and assessment of this type allows the designer to focus on the most hazardous areas when designing a mitigating solution. They also allow the designer to understand the extent and the modus of instability processes, which, if you remember, was the first step in the project initiation stage. The software we used, or the model we used here, is called plant-based and comprises specific detailed design protocols and routines which can be used in design for stability while accounting for the spatio-temporal distribution, hydrological effects, mechanical effects of vegetation, anything of this sort within the eco-engineering project. These protocols and routines are based on commonly accepted engineering principles, but are not specifically associated with any national or transnational standards at the moment. Future efforts will be focused on translating this into Eurocode language and synchronizing them with the relevant national standards. Notwithstanding this, the plant-based model is capable of determining the optimal vegetation characteristics which would provide stability and sustainability against hydrometeorological hazards such as rain-induced shallow landslides or erosion. These characteristics include root system morphology, branch or crown architecture, their respective contributions in mechanical or hydrological reinforcement, etc. It's interesting that the most sensitive vegetation characteristic deployed for soil stabilization turned out to be the root system morphology and the crown area, which both of them reflect mechanical and hydrological group of vegetation effects. While the crown area is relatively easy to measure and monitor, the importance of specific ground investigations come to the fore yet again when attempting to determine the root distribution laterally and in depth. However, with frequent use of this model, the engineer would be able to learn that different plant species might be suitable for different types of slope protection, depending on the hydrological conditions, for example, wetting or drying, or mechanical or environmental conditions. This suggests that botanically diverse slopes with different plant functional groups are desirable for a more effective soil protection. We learned that in general, and from a geotechnical viewpoint, if you like, underweight plants with dense root systems and broad, thick canopies would be suited best for the stability, sustainability, and resilience. The traditional design, civil engineering design, if you like, is a two-phase affair. The designer makes a plan before acting on it. And because the designer or their clients had made all important decisions in advance, they have to worry only about the means rather than the ends while carrying out the plan. In this process, there is little risk and little afterthought, which as a consequence tends to become a routine. For eco-engineering designers, the conception and execution of works go hand in hand and are so interdependent that they can't be separated one from the other. Whereas the traditional designer only attempts only what they know is possible, the eco-engineer is always tempted to attempt the impossible, or at least the improbable, or unimaginable, because of the lack of knowledge of the processes going on, for example, in the nature below or above ground. This is why the spatial coordination of the NBS projects is very important in ground bioengineering projects. Traditionally, specialist and highly qualified labor and or specialist construction would have to be mobilized to and from the construction site, making sure the environment is disturbed as little as possible. The NBS projects, which have designed with vegetation in its core, can greatly improve the sustainability by the use of locally available labor, locally available construction materials. The fact that native vegetation will always be preferred to exotic species allows for collection and use of it in the construction. A recent work with colleagues from Spain and Italy saw us designing similar NBSs for two contrasting environments, a sediment retention check dam in Asia and a similar type of structure in Spain. The solution was dictated by the hazard type. In both cases, erosion was the issue, either in a fluvial environment or in a post-wildfire forest environment. Both solutions relied strongly on locally available native species, which were implemented in the solution to provide reinforcement and strength in the long term, together with locally available, recycled, inert materials, which would provide stability and strength in the short term. For both projects, we developed protocols and routines for design and mobilization, demobilization, which work at provision of decent work for the local workforce while reducing inequalities in broader context. These protocols are based on the existing European guidelines and can be further used to develop an innovation in terms of a common ground bioengineering specification, which will enable transnational visibility and use. The construction project stage, perhaps the most critical for the success of our ground bioengineering project, should be carried out only by professionals who are suitably trained in the specifics of both civil engineering and plant science. As remarked by a number of professionals surveyed during the EcoMed projects, such workforce would be able to respond to changes in the design or climate conditions very quickly without compromising the overall sustainability of the project. Cognizance should be given to the vegetative period of the plants employed in the project, as well as to the potential interaction between the living environment, animals, insects, bacteria, birds, etc., the climate, drivers like wind, rain, solar insolation, etc., and the inert and living construction materials. The existing specifications for construction can be used together with the experiences from previous projects in order to minimize the time needed for construction, but also, very importantly, to train the workforce. The construction of nature-based solutions doesn't differ greatly from the construction of traditional civil engineering measures. The major differences are in the philosophy of the design, which for NBS allows a temporary construction or structure to become permanent and thus increase the sustainability and resilience value of the project. One example of this philosophy is the construction of, for example, live drains, which would be used as temporary drainage structures during construction, but will continue to function as permanent, as drains, once the live material within them has rooted and started to provide stability and reinforcement to the surroundings. Another example is the construction of temporary drainage for linear civil engineering projects. The silt pollution generated during major highway works can prove detrimental to the water environment and the aquatic species that depend on it. Construction activities can leave many kilometers of exposed soil susceptible to erosion, either from surface water runoff or similar, which can result then in silt pollution and degradation of ecologically sensitive watercourses, if appropriate mitigation is not in place. However, different temporary drainage measures have different space requirements, and some of them can be used only as temporary, while others both as temporary and permanent measures. In a recently completed knowledge transfer partnership project, Jacobs and GCU developed a methodological framework able to estimate the required capacity of soil and water bioengineering features, such as settlement ponds in this case, based on runoff and soil loss estimation. The application of the framework in a case study showed viability and highlighted that improved accuracy of the site-specific parameters is needed in order to increase the robustness of the framework. Furthermore, this framework demonstrated how adopting different erosion control measures can reduce the land required to accommodate gray, blue, and green infrastructure solutions. Accurate, relevant input parameters about not only the geoclimatic drivers and variables, but also about the design and construction works, as well as earthworks, vegetation, water parameters, all of them can be obtained through ground investigations and or in situ or laboratory testing. Minimizing the land take contributes here towards more responsible construction and decreases the consumption of materials during a civil engineering project. Due to the specifics of design and construction with vegetation, special care will have to be taken during the early stages of operation and maintenance of these projects, when the vegetation needs to develop the below ground and above ground parts, which then will perform the engineering functions in the long term. Frequent inspections and surveys should be done at this stage in order to record the development of the green infrastructure. Relevant data should be collected from these surveys and fed into numerical models able to assess the stability, performance, sustainability, etc. of the life structure at different development stages. This can be contractually regulated by including a maintenance contract or subcontract in the project documentation, a part that was highlighted as currently significantly lacking across the EcoMed case studies I talked about previously. Exploring the bioengineering potential of energy crops that can be used for transport fuels or heating, electricity generation is one potential innovative sustainable strategy. The fact that the soil strengthening properties of, for example, willows or poplars, often used as short rotation copies, are relatively well known, gives rise to the possibility of other vegetation, such as grass cut during the maintenance of the existing transport network, as shown in the table here, being used to both provide resilience of the infrastructure against the effects of climate change, while also providing a source of sustainable energy or food. Another innovative sustainable aspect at this stage of the project may be the use of phytoremediation potential of some vegetation types, which can be employed on different brownfield sites. The graph on the right shows the results of a recent laboratory study we did on the potential of ferns and alfalfa to filter gully goo pollution from the soil. The maintenance and operation of the ground bioengineering assets will be associated with an increase in employment and wider stakeholder engagement, which in turn will contribute towards minimization of poverty, and in cases where private residential properties are at risk, which is managed by the infrastructure owner, will foster the sense of justice among the affected population. The success of a large-scale ground bioengineering project will ultimately depend on the partnership of a wide range of stakeholders, including the general public and the full supply chain. And the civil engineering in charge of such projects should have the awareness, knowledge of these specifics in order to successfully manage projects of this sort. One of the major gaps identified in the analysis of the case studies from ECOMET project was the lack of monitoring and the long-term sustainability design. In contractual terms, it is important that the temporal scale of the vegetation effects is acknowledged through planning for the full project life cycle. The focus should be the sustainability of the project in the long term, so adequate, relevant maintenance and monitoring carried out by suitably skilled professionals should be included in the contract. Adequate and relevant monitoring should include then integrated, real-time, multidisciplinary measurement and analysis of the parameters critical to the stability and sustainability of the installed structure. These would supplement the standard geotechnical or structural monitoring by incorporating relevant measurements of the vegetation parameters, and would also include periodic sampling and in situ or laboratory testing. Draft protocols and specifications for monitoring of NBS exist and can be used together with monitoring information. For example, for a number of years now, we have been including a range of stakeholders in the monitoring of our eco-engineering project sites, and we have been applying citizen science concept to get the stakeholders closer to their local environment while collecting important scientific data, which we then use in design and modeling of the ground bioengineering solutions. When designing the monitoring program, the engineers should be guided by the BIM standards, Built Information Modeling, and the digital twin or Gemini principles, which allow or will allow for more efficient life cycle management of the installed measure and safe decommissioning at the end of the life, both of which will contribute to the circular economy objectives. Due to the specifics of using vegetation in engineering applications, decommissioning should not be understood in its classical sense. The eco-engineering ethos envisages the vegetation taking over the engineering functions of the green infrastructure in the long term, while providing suitable environment for enhancement of the engineering function and vegetation succession. Due to this, the engineering design needs to take into account some specifics of the long-term behavior of the vegetation. As mentioned previously, the vegetation needs care and maintenance in the short term until the engineer is satisfied that the physiological functions have been established and the live materials are thriving. Once the roots and the above ground parts start to grow, the vegetation would be able to take a proportion of the loads imposed on the structure. And then with time, the inert materials, which may have been used as protection for the vegetation and structural support in the short term, will start to decay, erode. During this transition period, which depending on the type of materials used, can range from months to decades, the vegetation will take over the main stabilizing and supporting function for the structure until the point when the inert materials have completely decomposed or eroded and all the loads are taken by the live parts. This process of load transfer can be captured in the design by allowing for the decay of the inert materials and root system development at various stages in the life of the project. In the past, we developed a framework and protocol for design checks that would allow for the vegetation effects and also durability of the inert materials in a slope stability context, which can be used in any eco-engineering design project where a combination of live and inert materials is envisaged. Another specific of vegetation behavior in the long term is the resilience it provides through ductility of the root soil continuum. Soil tends to fail in shear for example, during landslide, at a very small displacements, while the roots are able to withstand large strains before breakage. The combined material, the root soil continuum, will therefore tend to be ductile with a behavior characterized with a failure of the soil component at small displacements, followed by a creep, if you like, of the roots as the strains increase. During this movement, some of the roots in the root system will stretch, others will bend, others will pull out, and others will break, until at very large displacements, all roots have failed and there is no support for the displaced soil mass. In an attempt to synchronize the behavior of both elements in the root soil continuum, we developed another protocol for design checks that takes into account the ductility provided by the roots. When applied to a slope stability context, you see this in the middle here, this approach will include identification of zones where the soil root continuum has failed locally, then calculation of an interim safety factor for the slope, and finally, assessment of stability based on the strength the roots only can provide to the rest of the failure surface. The assessment of the long-term impacts as well as sustainability of eco-engineering strategies can be challenging and remains neglected largely within the literature and in practice. The challenge lies in the achieving a balance between the delivery of the project objectives and their alignment with the principles of sustainability, resilient design, which will seek to provide an appropriate and satisfactory environmental and financial performance while delivering social benefits. Whilst it's possible to assess various aspects of the long-term performance of soil bioengineering measures and the relevant projects in their delivery through cost evaluations, risk assessments, environmental impact assessments, as we all know from the industry, there is no standard means of assessing the sustainability performance of NBS solutions in an integrated framework which will capture the environmental, social, economic dimensions of sustainability. To address these issues, we recently proposed an integrated sustainability assessment framework which can be applied on any eco-engineering project. This framework is underpinned by a review of sustainability indicators commonly applied in different assessment methods and best practice from relevant civil engineering disciplines. This framework includes a set of key performance indicators, KPIs, reflective of the both engineering and sustainability requirements for eco-engineering in the context of stability, active use of vegetation, and long-term sustainability. The unique nature of each eco-engineering measure and its provision is established here within the framework with contextual indicators which sit within the environmental, economic, social, but also engineering set of indicators. We have demonstrated the application of this framework on a completed coastal slope stabilization project, the results of which you can see here on the radar plot. And we are working on similar assessments for eco-engineering projects across Europe. This approach allows the engineer to use the framework as a planning tool at the early stages of the project, but also as a double loop learning or lessons learned learning tool after the completion of the project. The use of the framework as part of an existing quality assessment, quality management procedure is convenient because it comprises a number of KPIs which are already being measured as part of other QA processes. The eagle-eyed amongst you would have spotted that one of the SDGs is missing from my mapping against the stages of the project. I deliberately left the SDG 4 for last because I believe that education is the basis of a wider, broader adoption of the eco-engineering approach. In order to sketch the roadmap for the soil and water bioengineering sector within the EcoMed project, we asked students, graduates, professionals, practitioners to reflect on the gaps in their education which could be filled in with additional training. The results, broadly summarized here, show that more training is needed on the design and planning with vegetation, as well as on a range of digital and specialist skills. Early in the talk, I tried to demonstrate to you that both knowledge and expertise in design with vegetation exists, and it's readily available for designers and practitioners. I also mentioned the application of some digital technologies in the design, such as the use of GIS and the big data concepts. The current efforts of the soil and water bioengineering research community not only through the academic institutions, but also through the, for example, European Federation for Soil and Water Bioengineering, are concentrated on the enhancement of digital skills among the practitioners in light of the Industry 4.0, for example, and the project lifecycle processes. The progress, however, is relatively slow and somehow reflects the progress in digitization of the construction industry, where specializations such as master's degrees are considered useful for achievement of personal and corporate goals. It's worth highlighting that the vision for the ground bioengineering sector outlined above can only become reality if relevant, timely, and quality education for all project stakeholders is available. Where and when this education is best placed? Undergraduate courses in ground bioengineering or soil and water bioengineering are sparse across Europe, although the increase in application of the approach has been steady, especially in the Mediterranean and Alpine regions in the past 2 decades. The efforts of colleagues in Austria, Germany, Portugal, to name but a few, who managed to run specialist ground bioengineering courses are of note, as opposed to the majority of universities who, because of the multidisciplinarity of the subject, include the soil and water bioengineering subjects in the curricula of not only civil engineering, but also agriculture, forestry, architecture, environmental studies, etc. Bearing in mind this diversity of backgrounds that eco-engineering encompasses, perhaps more focus should be given to upskilling within the civil engineering and construction sectors in order to strengthen the skills base and promote innovation. Master's courses or targeted and specific continuous professional development courses, where academia would provide the multidisciplinary theoretical and the industry the practical formation, may be the most practicable option. Similarly, considering green infrastructure as a socio-technical system, the communities and stakeholders affected by ground bioengineering works should also be educated in order to foster discussion between the infrastructure industry, government, society, stakeholders, etc., about what outcomes are desired from that infrastructure and recognize those outcomes as the objectives for the industry. In this respect, the efforts of the European Federation for Soil and Water Bioengineering are of note. A number of projects funded by the European Commission, such as the EcoMed project shown here, also provide a range of resources for both online and offline learning. I would like to now wrap up this whistle-stop tour of ground bioengineering design by highlighting a few points which hopefully I managed to make during the presentation. My main message to you as decision makers and leaders who can make change not only to the profession you practice, but also to the world we all live in, is to embrace the ground bioengineering approach in green infrastructure and nature-based solutions without losing sight of the United Nations Sustainable Development Goals. I believe that only with broad awareness and acknowledgement of the benefits this approach can bring, we can successfully combat the climate change challenges, especially the ones connected to sustainable energy, as well as minimizing hunger and poverty, where ground bioengineering can potentially provide more benefits than the traditional civil engineering approaches. To effectively achieve these benefits, however, civil engineers will need to further enhance and implement the investigation, design, and construction procedures to include for the effects of vegetation. Similarly, more focus should be given to the maintenance and monitoring of the ground bioengineering structures in order to ensure long and sustainable life cycle. The good point is, however, that evidence and knowledge exist locally, nationally, and very importantly, internationally, which you, together with your clients, stakeholders, the general public, can contextualize and enhance with further application and practice. Perhaps most importantly, don't forget to reflect on each eco-engineering project after completion, not only to measure the success in sustainability terms, but also to learn and continue your professional development. Allow me now a few moments, please, to acknowledge the help and support I received during the last 2 decades of research and practice. The time doesn't allow me to name each individual and organization, and I apologize to everyone for this, but I would like to thank my academic colleagues and collaborating researchers with whom we continue to make contribution to the knowledge of this multidisciplinary subject. Also, I'd like to thank colleagues from civil and geotechnical engineering industry for their patience when listening to my incessant ramblings about trees, grasses and shrubs, which at some point earned me the unique title of industrial gardener. Great thanks also goes to the members of the communities who worked and still work with me for their hospitality, but also openness to new concepts. Also thanks to all partners and stakeholders on the collaborative projects who share the green vision with me. And finally, thanks to my family for their continuing support and encouragement. With this, I will thank you for your attention, and I'll be ready to answer any questions from the virtual floor.
Thank you very much, Bobby. Okay, so we have one question that's came in, and this is from Professor Cam Donaldson. So I'll just quickly read that one out. So he has asked, when discussing project initiation, you mentioned a prioritised action framework. I wondered what information or criteria that framework is populated by.
It has wide-ranging criteria that span the whole environment, if you like. At the moment, there's not much engineering in it. There's no many engineering criteria in it, but that's why we are here as civil engineers, ground bioengineers, to press with the decision makers, to press with our colleagues from environmental sciences, and of course with the communities, to include those in the EAPs.
Okay, and we'll just quickly take the last one before we hand back to Professor Cam Donaldson. So the last question was, you mentioned some work in Aberdeenshire. More generally, how does Scotland perform internationally in adoption of such exciting schemes?
Scotland can be considered a leader in international adoption of these measures. And we will continue with this adoption in order to keep the position that Scotland has at the moment.
Thank you.
Of course, the efforts of colleagues in England and the rest of the UK cannot be forgotten. We do have quite a lot of things going on in Scotland.
Thank you, Bobby. I'll just pass back to Professor Cam Donaldson just to close things up.
Okay, thanks, Lynn. So last opportunity if anyone does want to come in. Michael.
Professor, I sent a question to Bobby on the chat.
Let me just check in. Thanks for attending.
Thanks for the lecture.
After
Even
years
I
of
understood
failure,
most of it.
Can I read it? After
Yes.
years of failure, can you posit a possible solution to the constant landslides above the A83 road at Rest and Be Thankful in Argyllshire? Thank you, Ian. Very important, very relevant question. And the answer is yes. But
What
we don't have the time.
Observation. That's brilliant.
We don't have the time and space here.
Yeah, well, that's great, Ian. That would be great if that's lots of people. That would make lots of people very happy. Michael, did you put your hand up?
Unmute yourself, Michael.
You
please.
need to unmute yourself.
Thank you. Yes, thank you for that, Bobby. It's just a simple question, but do you have a favourite plant that you like, and why is that? I know that different plants is suitable for different contexts and different situations, but is there one that you like in particular?
Generally, yes. The pioneer species are great for all the work we're doing. So willows, poplars, and this sort of stuff. But my favorite plant will be the ideal plant, which, as we said, it's going to be very lean when it comes to weight. It will have very thick roots going deeper and laterally away from the stem, but also thick crown for interception, etc. So I'm sure if we go into details, we can find a plant or plants that will fit that description, but that would be my favorite.
Okay, thank you.
Thank you.
Okay, folks, we're running out of time, so I think we will have to call it a day there. Well, first of all, I'd like to thank Lynn and Jill for organising this event. It's gone really well, but I also want to thank Bobby's local and international colleagues for joining us for the lecture today, or what is now tonight. I mean, these, as Pro Vice Chancellor Research, these talks never disappoint me, and this one has been absolutely no exception. I didn't realise I was kind of making a huge underestimation when I said that several of the Sustainable Development Goals would be touched upon. Bobby, I didn't realise you were going to do them all, which was incredible. It's never been done before in these talks, and I'm not sure it would ever be done again. But I think it was, in that sense, and many others, it was a tour de force in showing this that indeed that soil is the route to a solution. So thank you very much, Bobby, for that, and thank you everyone for joining us, and I hope you have a good rest of the evening. Thank you, folks.
Thank you all.